Good afternoon, everyone. The 117th Distinguished Research Lecture will begin at 4 o'clock. Thanks for joining us. The presentation will begin shortly. Hello, and thank you for joining us today. We'll be starting the presentation at 4 o'clock. Good afternoon, everyone. Thank you for joining us for today's Distinguished Research Lecture. Before we get started, let's review a few housekeeping items. First, all attendee lines will be muted throughout the call. We do encourage questions, which you can send using the Q&A function on Zoom at the bottom of your screen. We expect to have a little time left after the presentation to respond to questions as time permits. Today's session will be recorded. As soon as the recording is available, we'll share it with everyone registered for this webinar, and we'll also post it to the Research and Innovation Office website. And now I'm pleased to introduce Vice Chancellor for Research and Innovation, Terry Fees.
Thank you, Chris, and thank you all who have joined us today. We're really excited to welcome you and to have you be part of our 117th Distinguished Research Lecture. Before we get started, I'd like to recognize and welcome Regent Leslie Smith, who is also with us today. The CU Boulder Distinguished Research Lecture is one of the most significant honors awarded to a faculty member each year. And this year it's exciting for the Research and Innovation Office because it's one of our own, Victor Bright, who's an Assistant Vice Chancellor for Research. And to get us kicked off, I'd like to introduce Russ Moore, CU Boulder's Provost and Executive Vice Chancellor, to tell you more about our speaker and the lectureship. Russ?
Thank you, Terry, Vice Chancellor Fees, and thank you all for being here today. It's a real honor for me to participate in this introduction. The Distinguished Research Lectureship recognizes a faculty member who has demonstrated world-class contributions in teaching, research, and professional leadership. It acknowledges a faculty leader who epitomizes the ultimate positive impact of a truly well-rounded professor. Today, Dr. Victor Bright, Professor of Mechanical Engineering in the Paul M. Rady Mechanical Engineering Department and Assistant Vice Chancellor for Research, joins this prestigious list of influential scholars as the 117th lecturer. And now, it's my honor and privilege to introduce Dr. Juliet Gopinath, Alfred T. and Betty E. Look Endowed Professor in the Department of Electrical, Computer, and Energy Engineering, who will introduce our distinguished speaker. Juliet.
So I think my video has failed on my camera. So I will just do it this way. Thank you so much for the introduction. It's my great pleasure today to introduce Professor Victor Bright as the 2021 Distinguished Research Lecturer. He truly embodies the qualities of this high honor with his international reputation for academic excellence, as well as his outstanding contributions to education and service. One of my earliest meetings with Victor was in the engineering coffee shop over a decade ago. I remember asking him, do you have a system to deposit pyrrolene? Pyrrolene is a specialty material. We ended up in his office and jump-started a long-running collaboration on adaptive optical devices. These are elements that control light, such as lenses or prisms or mirrors, that can adapt to changing conditions or by varying their properties, and are obviously of great interest to Victor. At this time, I did not have any students or funding for the project, and Victor found a student and postdoc to work on the research to take us to liftoff. Our first funding came from a 500-word abstract that was entered in a contest, resulting in a prestigious grant. The investment of time and resources paid off, and today the adaptive optics projects enjoy widespread support in a range of application areas. Just to bring things full circle, at a recent pitch, Victor and I met the inventor of pyrrolene, and we found this out because the inventor has a dog that's named Pyrrolene. So Victor's research is marked by originality and insight and a synthesis of the theoretical, practical, and experimental aspects of mechanical and electrical engineering. Some of his most highly cited research has been commercialized. He's regarded as one of the leading figures in the field of MEMS, MicroelectroMechanical Systems. MEMS is a technology that represents tiny devices or systems that combine mechanical and electrical elements to perform a multitude of functionalities. They're fabricated using integrated circuit processing techniques and range in size from a few microns, 1/10 the size of a human hair, to a few millimeters, the thickness of a US penny. MEMS can be used for light-based or optical applications. These devices can be used to correct imperfections or turbulence from the atmosphere, steer optical beams around in free space for sensing, and in high-speed communications using light. MEMS can also be used to make miniature actuators that are similar to muscles in the human body, a part of a device or a machine that helps convert energy into physical motion. MEMS sensors are ubiquitous. One example are accelerometers, which are found in game controllers, cell phones, and cars. Victor is internationally recognized for his contributions to the areas of optical MEMS and MEMS packaging technology. He's particularly well known for seminal work in low-power laser beam steering, optical aberration control, and optical communications. Victor is also recognized around the globe for his development of microactuators based on thermal expansion. These have been used for surgical instruments, along with optical and microwave switches. The last decade of Victor's career has been devoted to his research on nano-electrical-mechanical systems, or NEMS, atomic layer deposited nanoscale sensors, and electrowetting adaptive optical devices. He was the first in the world to use atomic layer deposition and atomic layer etching to fabricate nanoscale sensors. Atomic layer deposition and etching are techniques that enable the application or removal of layers of atoms at a time. This is on dimensions of 1/1,000th the size of a human hair, and these techniques are ideal for nanoscale systems. Capitalizing on this, Victor's work on sensors has been pivotal in the creation of low-cost night vision thermal imagers. He has also made seminal contributions to the field of adaptive optics, specifically in the area of optical liquid lenses, prisms, and switches. His work has resulted in highly cited contributions in the fields of imaging, microscopy, and remote sensing. Light detection and ranging, or LiDAR, is similar to radar, but has higher resolution. It's important for all kinds of imaging and sensing, such as water monitoring and autonomous vehicle navigation. Here you can think of self-driving cars. Recently, Victor introduced a LiDAR system with 180 degrees of scanning using an electrowetting optical prism. Victor received his BSEE degree from the University of Colorado, Denver, and has an MS and PhD degrees from the Georgia Institute of Technology. He's a professor of mechanical engineering and an assistant vice chancellor of research at the University of Colorado, Boulder. He's held numerous leadership positions, including the Associate Dean for Research and Department Chair of Mechanical Engineering. He has over 300 publications in the fields of sensors and microsystems and has advised 67 PhD and MS graduate students in his career. Please join me in welcoming Professor Victor Bright.
Well, good afternoon, everyone. Thank you for this wonderful introduction. Thank you, Thierry and Ross, for all your support over the years. It's very much appreciated. And thank you, Juliet, for the great introduction. This award is very special as the nominations and selections are done by the faculty. And I am truly honored to be selected for this award. So let me start my presentation shortly. All right, so I will start with this introductory slide. And what you see on this slide here, on the right-hand side in the lower corner, you see a CU buffalo. And this buffalo is very, very small. It's on the order of the size of a human hair. And if you look at the left-hand side, you can see the fly, house fly wearing glasses. And when I show a picture of that fly to people, they typically ask, why does a fly need glasses? And the point here is not the fact that the fly needs glasses. It's the fact that we can actually make glasses that would fit a fly. So before I proceed, I'd like to thank some very, very special people in my life. So number one is my family, my wife, Julia, my sons, Ben and Charlie, my parents, Maria and Mark Bright. And I would also like to thank my students, all 67 of you. It seems like an impossible task to list every single name on one slide, but I'm truly honored, and it's been a pleasure and privilege to work with you over the years. So let me set the stage by showing this slide, which is evolution of technology. If you look from 1900s to mid-1960s, you see considerable change in the way the airplane would look, and you can see considerable change in the way a car would look, and the way they function, and the way they're built. But if you look from the 60s to the present day, you don't really see that much change, at least not on the surface. The change happens inside all the control systems and all the sensors that allow us to have efficient and safe transportation. In fact, if you look at a car these days, it has dozens and dozens of tiny little sensors. If anything from engine control to pressure sensors and tires, to navigation sensors, to displays. So all of this is present in the car, and it really is unfortunate when one of the sensors shows an error, right? And we're all used to that by now, yet the sensors make our life safer and cars more efficient. So this is evolution of technology. And then I thought, well, maybe interesting to show evolution of faculty. So I'm not even sure what exactly happened here, but I did join CU Boulder in 1998. Okay, so what are MEMS? So MEMS stands for Microelectromechanical Systems. Micro, M for micro, small, electro for electrical components, and M for mechanical components. And then systems really stands for systems like functionality. And what you see on the right-hand side, you see a little motor moving. That's a motor out of my research group. And that's an electrostatic motor that I will say a few more words about a bit later. So how small are these devices? Well, if you look at the US penny, it's about 19,000 micrometers. And we measure these devices in micrometers or microns. And if you look at a red blood cell, it's about 10 micrometers in size. So all the devices you're going to see today are about this size, definitely less than a penny, but about the size of a blood cell, and around about 100 micrometers in diameter, which is about the size of a human hair. Okay, so if you look at this type of devices, they all pretty much made out of silicon. So silicon is a semiconductor material that is used to make electronics, but it turns out silicon can also be used to make mechanical systems, and it can be used to make mechanical systems that are integrated with electronics. So a common example of that is atomic force microscope, where a micro machined needle is used to measure the surface profile of something. And what you see on the right here in the lower corner is you see an iPhone accelerometer. That's a device that's used for measuring when you turn your screen, for example, or when your phone drops. And you see on top here, you see a little structure made. It says CU next to an ant holding it. And on the right, you see a motor, a microfan that's also been fabricated by my group. And again, I will say more about that shortly. So the sensors have been shrinking over the years. What you see here on the left is the gyroscope device that's used for navigation in the aircraft. And you can see the size of a traditional gyroscope. And then mid-2000s, you start seeing devices being made in silicon. And these devices are about 1,000 times smaller than these macro scale devices, which would be millimeter type devices. And then this device here on the right-hand side is a device fabricated in my group, made in my group. This device is 1 million times smaller than your typical gyroscope. Okay, so the question that people often ask is, does miniaturization result in the same performance? So I like to use this chart. And if you look on this chart from right to left, this guy on the very right-hand side is built for agility and speed. And this guy on the left-hand side, on the very left, well, is built probably for cuteness. So how does performance change with shrinking dimensions? Well, it all depends on what specifically you are looking for in the performance. So for example, if we take a cube, and I promise this is the only slide that has any form of equations in it. But if you take a cube of dimension A, and we know that the surface area of one side is A squared, but the cube has 6 sides, so the total surface area is 6A squared. But the volume of the cube is A cubed. So if we take the surface to volume ratio, if we just take the surface area divided by volume, we'll get 6 over A. And similarly, if I take another simple geometric shape, such as sphere of radius A, the surface area is 4 pi A squared, and the volume is 4 pi A cubed over 3. So if I take a surface to volume ratio here, the surface area divided by volume, I get 3/A. In both cases, you can see that as A becomes smaller, smaller and smaller, the surface begins to dominate. It's the surface that really matters here, not the volume. So bottom line is this, the physics laws are all the same at the scale, but what happens is that smaller things are less affected by the physics of volume and are more affected by the physics of surface. So a few examples from nature. If you look on the left-hand side, the example I'm using here is surface tension. And you can see here these water bugs are able to walk on the surface of water simply because they have very small volume. They have a lot of surface area, but small volume, so their mass is very small. And the surface tension of water keeps them from falling through. And on the right-hand side is an example of what we call dry adhesion. A tiny lizard, a gecko, climbing on glass. And if we took a close look at the fingertips of this gecko, we see a lot of interesting structures shown here, tiny little hairs and cells. And the reason for that is the more cells it has, the more surface area it has for being able to walk on the surface. And so the atomic forces is what keeping this gecko attached to the surface. There is no glue involved here. It's just simply a lot of surface area upon contact. So the future is really small. If you look at the transistor was invented in 1947. And the first transistor was about 10 centimeters in size, which is about 3 inches, roughly speaking. And present day transistors are measured in nanometers, tens of million reduction in size. And today's chips have millions and hundreds of millions and sometimes billions of transistors on them. And similarly, we can reduce mechanical parts, as shown on the right-hand side. We can make very small gears and mechanism on the order of the size of a human hair. So the MEMS technology is growing. It's everywhere. We're all familiar with sensors in every single thing that we use, in every component, in every device we buy. The current trends in sensors are wearable technologies, environmental monitoring, virtual reality, various types of speakers, optical image correction, and so on. So a brief history of this technology is that it all started with Richard Feynman, who's a Nobel Prize physicist in quantum mechanics. And Richard Feynman gave this lecture in 1959, which he titled, "There is Plenty of Room at the Bottom." And in that lecture, he was wondering, how can we miniaturize a computer? Now you have to keep in mind that in 1959, computers were the size of a living room, based on vacuum tubes. And yet he was talking about his vision, how computers can be miniaturized, and that came through. And he talked about how things can be miniaturized by evaporation. To him, everything could have been made by simply depositing very thin films. So he was wondering what would be the possibilities of small or movable machines. And then he predicted that in the future, we should be able to arrange atoms any way we want to. And sure enough, in 1990, IBM demonstrated that indeed you can do individual atom arrangement to spell out IBM. Then in 1982, an IBM scientist, Kurt Peterson, proposed that silicon, which is a semiconductor material used for electronics, he proposed, well, why don't we just use the same material for electronics? We use it to make mechanical components. Why don't we make sensors out of silicon? So he was saying that we'll take advantage of the fabrication technologies already available of that industry for semiconductor. Silicon is abundant. It's everywhere. Silicon oxide is sand, so we know how to make silicon. And so we can combine this MEMS components, mechanics with IC technology all in one unit and make very, very small sensors and machines. So the key areas, or the key markets in this field have always been automotive and biomedical. These are the ones that have been driving the markets. Anything in automotive, from inertial sensors to pressure sensors to various types of chemical and gas control sensors. And in biomedical, you also see inertial sensors and pressure sensors, and a lot of disposable type of components for blood analysis and so on, as well as neural probes, pacemakers, and things like that. And so about 20 years ago, National Research Council published a study on emergence of MEMS and how it will penetrate every aspect of our lives. And I put that here because they put on the cover page here, they put a picture of the device from my research group. So we were happy to see that. So these days, where we are with MEMS in biology and medicine especially, is we start looking at some very interesting applications like smart contact lenses, various types of microphones and hearing aid, and of course, sensors are used inside the pacemakers. So the field is growing rapidly, and the field is really everywhere. So how are these devices are made? Just very briefly, they're made in the same technology as electronics. We start with silicon wafer, and we deposit materials layer by layer. And then we pattern these materials, these individual layers. We etch them to remove what we don't want. And as a result, we can repeat this process over and over until we build our three-dimensional structure. Once the structures are made, they are tested, and they are packaged and then sent into products. So this type of manufacturing allows us reduced cost. It allows reliability because the parts are made all the same. Because parts are very, very small, they take very little electrical power. So that's great. And then this type of sensors enable new applications. Just to show you a typical example of what this type of sensors may look like, if you look at the pressure sensor on the left-hand side, typically it's just a suspended membrane with a strain gauge on top or embedded in it. And as the membrane deflects due to difference in pressure, the strain gauge can measure that. And here below, you see a commercial product. And on the right-hand side, you see a schematic of accelerometer where we have a mass, what we call proof mass. This mass moves due to acceleration or deceleration. And it has, again, it has a strain sensor and a supporting cantilever that supports this mass. And so as the mass moves, the strain sensor measures the strain in the cantilever. And again, below you see a commercial product. This particular example is an interesting one. Here is an accelerometer that is actually very well known in the field because this was one of the first devices, first accelerometers used in airbag crash systems. So if you look at this device, it's very, very small. The actual die, the silicon die that has a tiny mechanical component in it, the whole thing is 3 by 3 millimeters. It's very, very tiny. It's about the size of a grain of rice. And here the mechanical component is shown something like this in the illustration where the mass moves left or right. And as it moves, there's tiny little fingers that measure the difference in capacitance as the mass moves. I joke a lot with my students is that here's an example where the mechanical part, the machine, is smaller than the electronics that are used to process all the information. But next time when you start the engine in your car, think about this tiny little device that is sitting behind the steering wheel and basically measures, keeps you alive in case of something bad happens. So MEMS is a disruptive technology. Basically, what that means is that this type of sensors allow new applications that haven't been thought about before. If you look at this diagram here below, you can see accelerometer been around for a long time, and that's a similar accelerometer to what I just talked about. But then in 2007, Apple introduces iPhone. And the moment they introduced iPhone, we start seeing more and more sensors being developed and being integrated into this product. So iPhone is actually an interesting example. It allowed use of sensors that were not used before in cell phones. So it created completely new consumer product. So now I'd like to move to some examples of sensors and machines out of my research group. Everything you will see here has been published and has patents on it. And we are very happy about this work and very proud of it. So I hope you find this just as interesting. So the first interest in MEMS when I started my research in this area was in actuators, micro robots, and self-assembly. So this idea of why do we need to make a very large robot that's super intelligent? Why don't we just simply make a lot of very small robots? They may not be very smart, but they can coordinate their motion in such a way that they can build something bigger as a result of that. And so think of it as an example of a bunch of little ants in a colony of ants where they all work together for a common goal. So here's an example from nature. Cilia in a respiratory tract. These tiny little cells, they move. And as they move, they actually move fluids along the channel, right? And so we can imitate that by making a machine such that this machine will have a lot of tiny little legs. And these legs can transport something in a conveyor type fashion. And so one of the earlier examples from my group is what you see here on the right-hand side. I'm going to play a little video. This is a tiny robot that was made in my group. This robot is 5 by 5 millimeters. So again, about a grain of rice in size. It takes very little power, and you can see for scale on top it next to an insect that it carries around. So you can see the tiny little robot move. It has lots of little legs underneath. And these legs are actually electrothermal actuators, what we call actuators that are based on thermal expansion. And so here on the left-hand side, you can see an actuator moving. And on the right-hand side, you can see an array of such actuators. And the way these actuators work is that if you pass electrical current through this flexure, which is shaped like an actuator, this thin area here, what we call hot arm, expands more than the cold arm. And so as a result, the tip of the actuator moves. This type of actuators can be assembled into more complex mechanisms. And what you see here is that you can see this type of actuator arrays driving a gear, which could be connected to some other mechanism. And down below, you can see these actuators driving a tiny little mirror sitting on top of a gear. And so you can see now how we can build very complicated systems that you can really see only under microscope. Okay, so the next type of actuators that we've been working on in my group is what we call electrostatic motor, electrostatic actuator. In the field, they also sometimes call scratch drive actuator. And so the way this device works is you have a plate that electrostatically is pulled down when you apply voltage between the plate and underlying substrate. So when the plate is pulled down by voltage, this tiny little toe moves forward one step. And now as you imagine, as you remove the voltage, the plate goes back into original position, but this tiny little corner, the step has moved the plate forward. And so as you drive this with repeated voltage, you can get this little thing to move to the right in individual steps. And what you see on the right-hand side is an electrostatic motor with tiny little plates that are driving this motor here. The other area of study that has been of great interest in the field is how to assemble three-dimensional devices. We know how to make two-dimensional devices by patterning thin films. And so, but how to assemble them is difficult. And so what we've been working on in my group is we use surface tension of liquid solder to pull up and assemble structures, self-assemble them. And what you see here in this video shortly, you will see how individual plates are assembled by tiny little shiny solder balls here. And the way this works, as you can see right above, here's the top view. You can have a plate that is connected to the substrate. Here's this cross-sectional view. And you have another plate that's movable. If you put a solder that overlaps both plates and you melt that solder at high temperature, the liquid tension of solder will try to pull itself into a spherical shape. And as a result, it will pull and assemble structures. So you can see already how on microscale and nanoscale, the surface tension force can be very, very strong. What you see on the right in the lower corner is you see a rather complicated structure made. And this structure here cannot be fabricated using any other techniques. What we've done here is we made the structure flat on the surface, and then we use solder. You can see 3 areas of solder here, 3 volumes that I used to assemble the structure. So the structure is assembled, you can envision it is similar to a pop-up type of children book, right? You just pull up the whole structure in one step. Now, this particular device, the electrostatic fan, this device has an interesting story behind it. We presented this device in an international conference. And that was in January 2001. And it turned out there was a reporter from New York Times sitting in the audience. We had no idea. And next thing you know, they wrote an article about our work in New York Times. And after that, it was very interesting because we started getting all type of emails and contacts, people asking about this microfan, various computer manufacturers been contacting us and asking, how can you make this microfan, and how can you make it thousands of them, or 10,000 of them to cool electronic chips? Well, it turns out you can't really cool electronic chips with this type of devices because the flow is rather slow. But it's an interesting device for measuring flow at a very low level and maybe doing some transport of molecules or gas or liquids at a very low level. So here you can see this type of device fabricated, the photograph of that. You can see individual blades of the fan are assembled using tiny solder balls. And here's the device running. You can see it running by itself. Again, this device is very, very small, just a few millimeters in size. And you can envision this a set of this type of fans used to pull some type of fluid through a channel. And what you can see here on the right-hand side is the smoke particles in air being moved. You can see this, it's very, very slow motion, sort of a laminar flow at that scale. So now I'm going to move to a different topic. So one of the areas that been of great interest to me and my students has always been optics. How can you do microscale optics? And what can you do with them? So one example of that is image correction. So imagine we have a distorted image coming into a system, and we have an array of tiny mirrors, and each mirror can be moved vertically in such a way that when we reflect this image from the array of mirrors, the image is corrected. Okay, so we were the first group to demonstrate this at a micro scale, and this was published in Optical Engineering. And since we were the first to demonstrate this concept of these mirrors at a micro scale level, it was also, our device was also used for the cover of that journal. Now, this technology is used at a larger scale in telescopes, but Doing this at a micro scale is completely different thing. And so here, what you see on the right, here on the right hand side, more in the center, you see a fabricated device. And on the right hand side, you can see a video of individual mirrors moving. And so these mirrors move electrostatically. And as a result, this device takes very, very little electrical power to operate. Applications of this are large. We can see optical communications, image correction, just as I mentioned. People are even talking about eyesight correction, smart glasses, and things like that. So the other area that's been interesting is making tiny loudspeakers using this technology. So everyone should be familiar that how you make a speaker. You have a diaphragm, a moving diaphragm, shown on the left and shown on the right. And so what happens, there is a coil, what we call a voice coil, and when you pass electrical current, it generates magnetic field around the coil. And that magnetic field interacts with a permanent magnet that's sitting behind this diaphragm. And as a result, you pull the diaphragm in and out, and so you create a sound pressure wave that propagates out of the speaker. Well, it turns out that on a micro scale and nanoscale, you actually don't need to have any moving parts. You can have an array of tiny beams. They are not moving, but you can have thousands of these tiny little beams. And when you send electrical signals through the beams, they heat up, they get warm, and then they transfer the heat to the surrounding air. And as a result, the surrounding air expands. So you have expansion, pressurization of the air. And as a result, you get a sound wave propagating out. And so what I'm showing here is an example of 3 such tiny speakers. And what I'm showing here is that speakers can be driven slightly out of phase with each other. And as a result, you can actually steer an acoustic beam, as shown in this simulation. You can steer the beam in space. But imagine you have many more of these speakers, all on this one little chip, microchip. And so then you can really have a focused sound that propagates in a specific direction where you want it to be. And so one can say, well, what is the point of that? Well, an example of that would be, imagine yourself in a room and you're attending a party and you're talking to somebody and everybody's around you talking, all the couples are talking, but all of a sudden, I can send you a message, I can talk to you. Only to you, only you can hear it and nobody else, because I can send a directed sound specifically to you. So what I'm gonna do here, I'm gonna try to play a small sound clip, how these devices work. I hope you can hear it well. You can definitely hear that it's a tiny speaker. So you definitely can hear the sound is not the same as you would get out of a larger speaker, but it works just fine. Okay, so now I want to switch to a completely different topic. So thermal sensors and thermal imagers. As I mentioned earlier, optics has always been of great interest in my group. And so this is something we've been working on for the past 15 years or so. When we typically look at optics, we look at the visible spectrum here between 0.4 micrometers and 0.7 micrometer wavelengths. But if we are trying to look at a thermal image of something, radiation of heat, we are really interested in this region here between 6 micrometer and 16 micrometer wavelengths. And the structures we make look something like this, as shown in the left lower corner. You can see individual pixels, individual plates on the left, and then on the right, we see our device, which is one just showing 1 pixel, sort of a tiny umbrella. And the way this works is infrared radiation comes in, and this tiny little plate is suspended. So infrared radiation comes in and gets absorbed by the plate. And so its temperature rises locally. And as the temperature rises, its electrical resistance changes. And we can measure that electrical resistance change. So now imagine if I have a whole array of these tiny pixels, each one of them will give me a different electrical resistance as a function of temperature, right? That of the heat absorbed by this plate. And so I can reconstruct a thermal image as shown on the right-hand side of this person here. And in this image, the brighter areas, the white areas is when indicates something warmer, and the darker areas indicate something that is colder. And so with that, you can clearly see a person. And this would work even during daylight because we are not interfering with visible radiation. We're just looking at the thermal image. So this work has been sponsored by Drs Technologies. It's been fascinating work to work on. And you can see here on the right-hand side, on top is my student, one of my students jumping in the snow. And I'm going to show you here below a video of one of my students driving a car in the snow. And you can see the person's walking at dark, it's complete pitch dark, gets in the car, you can see all the temperature differences in the car, and driving. And the fascinating thing here is not really the way this person drives, but to me, the fascinating thing is you can see the snow melting below the tires, because the melted snow below the tires is a little bit at a higher temperature than the surrounding snow, so you can see that. Okay, so applications of this type of technology are huge. And so here's an example of an automotive application from BMW, a night vision camera, infrared camera. It can detect a person in front of a car up to 300-meter distance. So the other topic I'd like to talk about is liquid optics. And again, all of us are familiar with this example. So here we see a water box, water beetles on top of a liquid, on top of water. They don't fall through. And what holds them in place is surface tension of the liquid. And on the right-hand side, you can see a water droplet on a fabric. Again, the surface tension holds the liquid together in a small droplet. Well, if you look at the droplet, this droplet makes what's called a contact angle with the surface. That determines the shape of the droplet for a specific material on which the droplet is sitting on. So you can see that example here. This is very hydrophobic surface. But it turns out that if you apply a voltage, electric potential to the droplet, and this is just water as an example. If you apply voltage to this droplet, you can actually change the surface energy of the droplet. And as a result, it changes contact angle. And so with applying voltage, you can make the droplet change its shape, as shown in the video below. You can see the droplet begins to spread as we apply voltage, okay? Now, what can we do with this? Well, here is one example from Pixar. What you can do with it is you can take a liquid droplet, a water droplet, and you can make a tiny telescope out of it. And people have actually used this technology to make cameras, tiny lenses that are voltage controlled, where the droplet shape can be changed. And as the droplet shape changes, as you can see in this slide right here, if I send an image through this, it looks just like an optical lens, like a glass lens would look, except now it's made out of water. And by changing its shape, I can do focus, defocus with that lens. So lots of interesting applications for something like this that is compact and takes very little power. And you have to keep in mind that liquids have perfect surface. You cannot manufacture a piece of glass with the same level of surface roughness as just a liquid droplet. So this type of devices can be used for lenses and prisms. They can be used to move droplets around. They can be used for communications, imaging, optical switches, and so on. So more examples from our research. Here's a fabricated microlens device. It's filled with two liquids. Typically, we use water and oil. We use two liquids so that they do not mix. And what's important here is this interface between the two liquids. You can see here in the diagram on the upper left, you can see the interface between the two liquids. You can also see the interface between the two liquids in the video below. Now the electrodes, the electrical electrodes are shown here in yellow on both sides. And the electrodes are actually made out of transparent material such that you can actually see what's happening inside this liquid lens. And now when I apply voltage, if I apply the same voltage to all the electrodes around the lens, you can see in this video below on the left-hand side, you can see the interface changes shape as I apply voltage. And now, as you can imagine, if I send an image or a laser beam through, I can focus, defocus that light as it gets through the device. On the right-hand side here, you see a schematic of this device looking from above, but now you can see 4 yellow electrodes. And when I have multiple electrodes, I can apply voltage, different voltage to different electrodes. And as a result, I can make a prism because now, instead of focus, defocus, I can tilt this interface. And when I tilt the interface, the laser beam that will go through will deflect left or right, depending on how I tilt this interface. And you can see it in this video on the right-hand side. Just pay attention to the interface. You can see here how it's being tilted. Okay, so that would be an example of a prism. And so if you can make a prism, then you can make a scanner, a laser scanner. So you can see here we can do raster scan with this type of device. And we can do also a spiral scan. And if you can do different type of scans, then you can produce an image that you like. You can program the device, drive it with a computer signal such that you can scan whatever image you like, pixel by pixel. Okay. And so this brings me to our current research. So this slide illustrates our current research. This is in collaboration with Juliet Gopinath's group in electrical engineering. It's also in collaboration with neuroscience group at CU Medical School. And what we are trying to do here is we are trying to build a tiny microscope. And this microscope is shown here in blue. It has the scanner that I just talked about in the previous slide. And it has a micro lens that's both scanner and the lens can be tunable. And then this device is attached to a fiber optic cable. And then the device itself can be attached to a living tissue or living animal. And we can look with light, we can deliver light through the optical fiber. We can deliver light and we can receive light. And so we can do neural imaging of live tissue. And here's an example, a 3D slice of neurons that we can see. And here is on the left-hand side is individual neuron. And you can see not just the neuron body, but you can also see its connections. And so this gives us resolution on the order of about 5 micrometers. So we are very much excited by this technology. This technology is supported by National Science Foundation, National Institute of Health, and everybody is excited to make this technology for science and for maybe even some commercial products in the future. So with that, this brings me to conclusion of my presentation. So I'd like to acknowledge The funding, lots of federal funding and industry funding went into all this research over the years. I'd like to acknowledge my colleagues at University of Colorado in Boulder, people who I've been working with over all these years. My colleagues at University of Colorado Anschutz Medical Campus, the neuroscience group. My colleagues at NIST Boulder, whom I've been working with, and also special friends and colleagues around the world. So with that, this ends my presentation. And I believe we might even have a few minutes for questions. Thank you.
Well, thank you, Victor. That was phenomenal. I love the history that you provided, as well as, you know, the state of the art and the amazing work that your group has done through the years up to present. So I'm opening this up. I think we have time for about 5 minutes of questions. So if you have a question you'd like to ask, please put it into the Q&A link, and I'll refer to that and pull questions from there. While we're waiting for people to ask questions, it's hard to ask questions because you presented so many amazing things. It's like, where do you focus? But let me start by asking you kind of a prediction of the future. You know, you talked about the iPhone in 2007 really became almost an enabler for so many more sensors. Of course, people were working on them prior to that, but it became a place to consolidate a lot of those commercially. If you look out 10 years, what's the most exciting sensor that you think is going to be part of our everyday lives?
Yes, I think that's an excellent question. So let me go back to the previous slide. This slide right here. This is what we are really, really excited about now. This whole field is called optogenetics, and it's opportunity for us to communicate with neurons, whether it's in the brain or peripheral nerves, without penetrating the skin. In principle, that's where we are going. And so rather than having robotics or artificial limbs where people use probes, electrical probes that actually have to go into the neural tissue to communicate with the body, imagine if you can just use light. Mm-hmm. So to me, that is the most exciting direction, that this man-machine interface without breaking the skin, that would be unbelievable. If we can do both reading and writing to the neurons, communicate with the body, it would really be incredible technology.
Well, that begs the question. So if you can do this non-invasive imaging, and you talk about reading and writing, what could you reprogram with this kind of technology, do you think?
Well, the obvious application that we are working with is the prosthetics at this point. People who would definitely benefit from, rather than having metal probes go inside the body. So it's not really programming the nerves at this point, it's being able to communicate with the nerves. Now, of course, one could envision the future where you could program something in the brain by sending optical signals in. I think it would be challenging to speculate where that may lead to. We can write a lot of science fiction books based on that, I think. But being able to understand how neurons function, how they communicate with each other for diagnostic purposes, for prosthetics, for medical purposes, for drug analysis, drug interaction, making people see again. If for some reason the optic nerve has just disappeared over time. You cannot make a blind person see if they didn't have an optical nerve to begin with that has developed over time. But if somebody loses their vision during their lifetime, the nerves are there. So being able to reach those nerves and communicate with them, I think that would be incredible technology. if we can get to that point.
Yeah, so it sounds like a lot of where you see the future of this is really helping with human health and really helping with people staying healthier longer and being able to impact that.
Yes.
So there's a question in the chat here. And this is by Chris Torrance. Looking back at Richard Feynman's paper, how close or how far away are we from things that he predicted could be done with nanoscale devices?
Well, at this point, that's a good question. I always ask that question of my students when I teach my classes. He pretty much predicted everything we could. A man with incredible vision. Very few people can look so far in the future, but he has been able really to predict everything we are seeing these days. And this man-machine interface that I just talked about, that's where we're heading. He didn't talk about that. This is new technology, the optogenetics. But miniaturizing the computer, miniaturizing the machines, being able to put atoms in place where you want them to be, all of that already has happened.
That's really exciting. We have another question, or maybe now all of a sudden they're coming in. So why would photonic simulation of neurons be more advantageous than electronic stimulation?
Sure. So we cannot get the same level of accuracy with electronic stimulation. So number one, if you put a metal probe inside a tissue, the tissue over time will reject it. It will push it out. It will grow some additional tissue around the probe. And as a result, after a while, the probe will not be able to interact anymore, measure anything. So because it's a foreign object, we don't want any foreign objects inside the body. That's number one. Number two, you cannot make an electrical probe small enough that you can get to the level of individual neurons, like we can principally get with optics. We just can't get the same type of resolution.
Great. Another question from Dan Powers. I recall a study that showed electrowetting being a factor in improved battery storage. Is that an evolving and needed use of such technology?
Well, it has been used in the battery storage. We haven't done it. We haven't done any battery work, but it is being used, and it is being used for more efficient wetting of the electrodes. Yes, indeed.
Well, we're at the end of our time. I just want to thank Victor for that outstanding presentation and sharing the amazing work that you and your group, and with Juliet too, have done throughout your careers. We're so proud of the work that you've done at University of Colorado Boulder. And I want to thank everyone who's been here today. And I know you feel like I do that this was a real treat to have Victor share all of this with us. So thank you so much, Victor, and goodbye, everyone.
Thank you.